All right. So, okay. So the topic that we're gonna study today, we will finish off this part on the PAC learning framework, so chapter 2. And then we will, I hope that we talk about something that we were in the middle of discussing, which is a generalization bound for the for the finite inconsistent case. And then we will solve some of the exercises. Likely maybe 1 or 2 exercises in the textbook. Okay, so where we are. So I have been talking about, let me erase this. So we have been talking about the definition of PAC. So here's a quick reminder. So we have been talking about notion of PAC, which intuitively means for any problem. So actually what I say is we have an algorithm. We have an algorithm such that for any problem instance, for any required precision, or any quality, if we have a polynomial, if the algorithm is given polynomially many samples, it will produce a hypothesis with a precision I think my English is not quite right here. Precision with high probability. So that's the idea. So for any problem instance, for any required precision, we just need to give polynomially many examples. The exact terminology was examples. Just need to give polynomially many examples. Sorry. If we do so, this algorithm will give us a good hypothesis with high probability. So that was the definition of a PAC that we covered. And then we said, and now we want to show some particular problem is PAC runnable. And then to talk about this, we learn about generalization bound or sample complexity bound. Generalization bound for finite and consistent hypothesis set. Consistent hypothesis set H. Roughly speaking, that's the polynomial that's required there. In this case, is going to be not actually polynomial. So the bound say something very similar to the statement of the PAC for any problem instance and for any required precision. If we give examples which are in the order, which have greater than the not square root, but greater than 1 over epsilon, and log of size of hypothesis class plus 1 over required probability. If that is the case, then we have this result. For any hypothesis H, the risk of H is going to be bounded by for any prop S H, if the RH of S is bounded by H if this R head of S is equal to 0. So then RH going to be bounded by epsilon, high probability of minus delta. And then this another way to say this, I mean in more general form, is the following. You can say probability of 4H, the R of H is going to be bound by, although we didn't really prove in this way, it's bound by 1 over delta. So that was our case in this consistent hypothesis. When hypothesis set is finite and consistent, then we are in the middle of proving something more general. And I said, in more general case, we may be in a situation where concept class and hypothesis class are not necessarily the same. In such a situation, we cannot really achieve the one that I wrote here, which is cannot really find hypothesis H with the, not actually this guy, hypothesis H, which have a very small probability. So because there may be inherent limits that we can reduce the amount of error. So to cover such a case, we were in the middle of discussing the more general version of this theorem, which also applies this consistent hypothesis set as well, which say that the following. I think some of you turned on the audio, so please turn it off. Okay. All right, so generalization bound for finite. And it's not necessarily inconsistent, but doesn't have to be not necessarily consistent. Hypothesis set H. And in fact, the form that we're going to have here is the one that will appear repeatedly throughout this course. And then that's often we're called generalization bound or uniform generalization bound. And the statement of the theorem is like this. So it's a theorem 2.13. Say that in a situation of the above, for any concept C, for any distribution, in other words, for any problem that any instance problem learning problem that we can think about, and for any required precisions and required probability, then we have probability that sample is e to the m for H. What we want to say is that we want to compare empirical error and the generalization error. Then for RH, the probability that for every H, the real generalization error is bounded by empirical error plus some extra, some quantity, which is given in this case is 2m over log of h plus log of 1 over delta. Probability that this generalization error will be bounded by this empirical error with this extra quantity is going to be quite high. So 1 minus delta. One way to compare what's going on here with the one before is to rephrase this statement in terms of the sample bound, and replace this part like this. Say if the number of samples, we can rewrite it like this. Say for all sample m, if the number of samples is greater than 1 over 2 epsilon square log of h plus log of 1 over delta. If that is the case, so then we have the probability that for h in h, R of h is bounded by that sub h plus epsilon is going to be greater than or equal to 1 minus delta. Okay? These two are equivalent statements. We can just replace the one, the marked one above, then with the marked one below. So just replacing this part and this part, these two things becomes equivalent statement. Now, once you do this replacement, you can kind of compare what's going on here with what's going on in the simpler case where we have a finite consistent hypothesis set. So in the finite consistent hypothesis set, if you just compare the two statements, the only difference is the sample lower bound. In one case, we have a 1 over epsilon and the rest, and then the other case here, we have 1 over 2 times epsilon square, because epsilon is a very small number, like 0.01. The required samples above, the required samples below is going to be a lot more. If it's, for instance, epsilon is 0.1, 1 over epsilon is 10, but 1 over epsilon square is 100. So the required sample below is going to be a lot larger. Okay. And the reason, you will see soon why that is the case. The reason is that in the one above, actually, if you see remember the proof, it's really the proof is based on the exponential improvement by repeated trial. So if you keep tossing a coin, the probability that all of those tosses will lead to head, the same result head, is going to decrease exponentially. So that's the core part of the core argument that we are using in the proof of this above generalization bound. But the one below, we are doing something different. We are using Hofstad's inequality, which is a different type of much weaker arguments about what's going to happen when it's take an average of independent bounded random variables and how fast it's going to converge to the average. So that's the, you can say it's a more sophisticated, but also much weaker bound that we are using, weaker kind of reasoning, a weaker bound that we are using. And that is because we have, this potentially inconsistent, it kicks in there. So we have to rely on this weaker argument. Because of that weaker argument, instead of having 1 over epsilon, we have 1 over 2 epsilon squared. And we looked at the proof of this 2.13. And then I said the proof uses Hofstad's inequality. So, this. So we are proving the proof of theorem 2.13. Then how the proof goes, and then the proof has 3 steps. essentially, the proof has a very similar form. We use uniform bound, and uniform bound means we remove this universal quantification for every hypothesis, and then we want to focus on the individual case. By using uniform bound, we go from all the cases in H into one specific case. And when we have a one specific case, we use one of the bound, like exponential decay argument or the concentration inequality. And so the key difference here is we are using some different kind of bound for each individual case. And then the key things that you use in this individual case is a Hopkins inequality. So it's a reminder of Hopkins inequality. So this Hopkins inequality says the following. It says that if we have a independent random variable x1 to xn, they are independent. I mean, they may be sampled from different distribution, but they are independent. And another important bit is they are all within some range between A and B. Okay. So that's another, I mean, without this requirement on the range, we can't really use this argument. So it's all bounded independent random variables. Then we are thinking about their sum. So use average, their average, which is 1 over m, sum over I is equal to 1 and xi. And then what this bound tells us, what's going to be the probability that this average, sample average, deviates a lot from from the expectation of this sample average. Well, people call this AM as empirical average. And then what's going to be the probability that this empirical average deviates a lot from their expectation. So then this Hopkins inequality say, we can actually know its probability we said is AM, which is a sample average, is quite large, much larger than their expectation. So sample becomes quite larger than the expectation by large. I mean, the epsilon is usually a small number, but we read it as a large margin. It's going to be bounded by this exponentiation of m epsilon square, and then b minus x square. So one thing you can notice in this bound is the use of this epsilon square here. And that's actually the reasons, the presence of this epsilon square is the reason why you see 1 over epsilon square in the sample bound in our statements. And the statements say the same thing. Then some say something symmetric, which said if AM is smaller than, far smaller than the probability that AM is far smaller than its expectation, which is expressed like this, it's also going to be bounded by the same quantity. There's 2. It's 2 and epsilon square b minus x square. Double check. So that's the Hopkins inequality. In our context, we have something quite similar to this xi. I mean, this xi in our context is going to be something which is for each of the sample xi, we can check whether our hypothesis for this sample small xi is equal to unknown concept class, that the output of the unknown output, the consequence. So, actually it's different. So that's the quantity that when we use this Hawking's inequality, this will become our xi. And then you can see that if I compute the average here, its average will correspond to what I call the empirical error or empirical risk over the samples, because h, because that's defined by 1 over m summation I is equal to 1 to m. Then this quantity. Okay. And then if you take an expectation of AM, so that's correspond to AM, and then expectation, this in our case will correspond to risk, because this, because that's equal to expectation of R above S. So this, and furthermore, in our case, A is equal to 0 because it's an indicator function, B is equal to 1. Okay. So what does that tell us? In our case, if we use this Hawking's inequality, then we can have this following corollary. Um, 2.11. This is say that the probability is about single hypothesis probability that if we have m independent samplers for the inputs, its risk is then equal to R above S H plus epsilon. It's going to be greater than, and let me write it in one form which is more close to what's written there. Then write a different form. So if the risk is not bounded by R head of S H plus epsilon, say that probability is going to be exponentiation of minus 2m epsilon squared. And how we can get this? This part, this statement is actually correspond to the statement above here. So if you move epsilon to the other side and expectation on the other side on the above statement, and then strengthen it, because the strengthen it is okay because we are computing the upper bound of the probability, strengthening by replacing less than equal by less than, then because B is equal to 1, A is equal to 0, we get exactly this amount. So based on the correspondence that I just explained. So this is just an instance of Hawking's inequality. And if you rewrite this Hawking's inequality in terms of so the exact form that we're going to use is a bit weaker form that goes like with the samples, and then the statement is have the following form. Say, sorry about this. There is a particular order of changing colors to change the color of the pen. Okay. The probability is equivalently same as a probability risk of H bounded by empirical risk plus square root of 2m log 1 over delta. That's going to be greater than equal to 1 minus delta. And I mean, you can obtain the one below by take very easily from the one above. You just take a 1 minus the exponentiation on one side and so on. And if you do some simple manipulation, you can get the one below. So they're talking about the same thing. Now, how can you use this 2.11? So point of the 2.11 is an argument about a single hypothesis. We say that when single hypothesis violates our upper bound, so I mean, if you plug in actually the one, I mean, this is that type of experiment. Single hypothesis probability, the single hypothesis is going to violate our upper bound. It's bounded by some exponentiation functions that we wrote here. Okay. That's what this is telling us. So now how can you use this to derive what we want to show? So it's quite simple. So once we know this, and then the fourth argument is essentially uniform bound. So there's a proof of the theorem. So how to prove this? So here's what we do. And then first we notice that it's sufficient to show negation of the probability that we care about. So that's the negation, say, probability that there exists bad hypothesis, which means in our there is a hypothesis H such that its risk is not bounded by the quantity that we want to use. So R so H plus epsilon. So I think the exact statement, the exact negation is this guy. So what is going to be so we want to sufficient to show that this probability, which means there is a really bad H. I mean, our statements say all the things in H are good. For all of them, risk is bound by empirical risk plus some epsilon. But this one said the probability that there is H, which is bounded by like this, is going to be n equal to delta. Then for epsilons, we are using this, which is log of H plus log of 1 over delta divided by 2n. Now, how to prove this? And proving this is not very difficult. We just use union bound. So this probability is going to be bounded by, if we just do the union bound for every H in H, probability of R of H is greater than its empirical risk. So our bound is not quite right. So the probability that our bound is not quite right. But then said that quantity is already proved here. Okay. So if we just use what we proved above, and this is it's going to be, sorry about this. It's going to be bounded by the summation of H, then exponentiation of minus 2m epsilon squared. But this, because exponentiation of minus 2m epsilon squared doesn't talk about anything on H. So, and then there are I mean, the cardinality of H, many terms that we are adding here. So that's the same as H of associations minus 2m. Now we plug in the definition of epsilon, which is given here. And that comes from the theorem. So if you plug in the definition, it's 2m log of H plus log of 1 over delta. And then this calculation cancels. Then if you do the calculation, that is exactly the same as delta. So for the proof, as I said, quite simple. We use a Hopf, as long as you are using Hopf-Dings inequality, the rest is quite simple. We use uniform bound to decompose our reasoning about everything in H. Well, in other words, we reduce the uniform bound into individual bounds. And then for the individual bound, we are just applying the Hopf-Dings inequality. And that's what we get here. And just like I said before, the regions, we have, instead of 1 over epsilon, we have 1 over 2 epsilon square. It's because of this use of Hopf-Dings inequality. And which you can also see we have 2 epsilons times epsilon square in this upper bound because of Hopf-Dings inequality. And that's why our bound is a bit different. Okay. Now so this is a general bound, and then many of the generalization bound that you will encounter will have the similar form. And what's the use of this generalization bound from the algorithmic perspective? The perspective of the algorithm, what this tells us is that if we have enough samples with very high probability, our proxy, which is the empirical risk, can tell us quite a bit about what's really going on in our real target, which is R of H. Of course, we can't really bound R of H by R head of S, but we have to put some extra select terms like the one here. But with the presence of the select term, we can talk quite a bit about it. Furthermore, if the we have exponentially many hypotheses, not doubly exponential, but singly exponentially many hypotheses, then the extra select that we are putting here is going to be polynomial in the size of the essentially size of the problem. Okay. Now one more bit, and if you compare this generalization bound with the one that you saw here, sample complexity with the one that you saw above, I mean the presence of 1 over epsilon square is dramatic. I mean that's also if you view it from the bound perspective. This means in order to tighten the bound, the order that of the samples required is square root of 1 over m, which is much worse than just 1 over m. Okay, so the much general case, getting some guarantee becomes more difficult. Okay, just one more. Although for theorem 2.13, is explained in together in the traditional setting that I'm have been using so far, which is called deterministic setting. The setting that I'm going to explain to you soon, which is called stochastic setting, the same theorem still works. And the proof is essentially the same. Now, what is the stochastic setting? The real world scenario, quite often, we are in the following situation. Okay. So instead of deterministic Z, which is function from input to 0 and 1, we have random C. Which means that it's a function which take care of X, and then you return, mathematical return probability distribution on 0 and 1. Well, more in terms of practice, what it does is that for each X, sometimes it typically tells us the right answer, but sometimes make mistake. That's because many of the observations that you get in practice have a noise. So it's not exactly for given inputs, in the real world, often the answer you get is noisy. You sometimes get 0, sometimes you get 1, but most of the time you give the right answer. So that's the typical scenario. So in that scenario, I mean, the PEC learning doesn't work. Okay. So in that scenario, PEC doesn't work. That's because the problem is that, I mean, the PEC is really requiring this risk. We want to, I mean, it requires us to find some H hypothesis based on the sample, such that its risk or generalization error becomes as small as possible. So if we want the error to be 0.01, the PEC say, I mean, all we need to do is just increase the number of samples. Then we can do it with high probability. So that's the setting where PEC can say anything. But if this R of H is lower bounded by, say, 0.001, okay, whatever we do, it's always bounded like this, then it's not PEC learnable. Whatever we do, we can't really achieve the requirements in the definition of PEC learning. And this stochastic setting is one of these cases. And actually the theorem 2.13 that we proved is also designed to address this type of case. Okay. So as I said, the theorem 2.13 applies in stochastic setting that I'm just going to explain to you. So then what's the formal description of this setting? The formal description of setting is, instead of having unknown concept C and distribution D over probability on inputs, we have just distribution D. I mean, it's using the same D, but it's defined different by input and output. So instead of distribution of inputs, and then the output is determined by unknown C, we have just probability distribution on D. And then the risk is defined with respect to this guy. Risk of some function H is to nothing but the expectations over, now it's a sample from, we sample X pair, and probability that H, I mean, didn't get this question right. So H of X is not equal to 1. That's the risk. Empirical risk, now the sample includes input output. The sample is a set of a sequence of input output pairs. So this is empirical risk of H, defined by 1 over M, summation is equal to 1 to M, indicator H of Xi not equal to I. So where S is sequence of X1, 1 up to Xn, Y. And so that's how it's defined. So then the question becomes how we should modify PEC, okay, so that it makes sense in this case. And then, as I said, the problem with PEG is it's really like a too perfectionist. It really requires us to reduce this risk as much as possible. So in this setup, where there are inherent lower bounds on how much we can achieve, how much we can reduce the risk, the modification that we have to do for PEG is to incorporate this lower bound. So that's the definition called agnostic PEG. These two. Okay. Vulnerability. Says the following. So we say it's not a concept, the hypothesis H is agnostically PEG vulnerable. if there exists an algorithm A and a polynomial such that for any problem, this time problem is just a distribution over input-output pairs. Any problem. For any required precision and required probability, any number of samples, if n is greater than this polynomial. So far, things are very, very similar. So here, small n is the size of the input. So then we have, we get some good hypothesis. The algorithm will return good hypothesis with high probability. Here, good means compared to the minimum that we can achieve. So this is a sample in compared to the minimum that we can achieve, the risk of H, S, which is returned by the algorithm A, is only slightly worse than, in the worst case, what we can achieve with the algorithm, which is minimum of H. R of H plus with high probability. So you can see the key difference here is we allow the possible mistake. Previously, this minimum has to be 0, but agnostic path learning, we are allowing this. There's some slack there. Okay. So this is definition of agnostically path learnable. And when I read the textbook, the part that I looked at doesn't really say very much about the agnostic path learning, but I thought it's good to know about this. And another good things to know about this setting, this stochastic setting, is the so-called Bayes bound and then Bayes error. Right. So here's a Bayes hypothesis. And Bayes error. So what are they? And then here we are asking the following question. So suppose, so far we are thinking about algorithms. So that's why we talked about the empirical risk and then some algorithms that work on the samples and so on. But let's do mathematics. Okay, so we don't care about algorithms here. We just said we know given a distributions, in the stochastic setting, we have a distribution D, which is probability over X and Y. And then this Bayes hypothesis of things only works when Y is very simple, 0 and 1. And let's also assume that X is finite. Otherwise, there are some issues, possibly some issues with measurability, which I don't want to talk about here. So X is finite. So in that case, here's the question. So suppose our hypothesis class is all the functions from X to Y. And then the question is, what is this guy, argument? H, which minimizes the risk. And then risk is implicitly parameterized by D. So this D is really influencing the risk definition here. So what is the solution of this? As I said, we do not really attempt to find an algorithm. We just want to give because we don't know D, but assuming we know everything, we want to see that what this one actually looks like. And also we want to ask, what is it going to be, this value of this minimization? It turns out we know both the answer for both cases, and answers are quite easy. And Bayes hypothesis is the solution of the one above. And the Bayes error is the solution for the one the next. So what is the Bayes hypothesis? Bayes hypothesis is actually quite simple. Given X, we are thinking about conditional probability of Y is having value 1 given Y. So Y is having value 1. Let's just call it A. So A can be either 0 or 1. We're thinking about this conditional probability. Okay? It's a finite, so Y has either 0 or 1. So its conditional probability can be computed quite easily. So we compute the conditional probability and return A that maximize this conditional probability. Okay. And that's called a Bayes hypothesis. It's a function that take input X, compute conditional probability, and return an output which maximize this conditional probability. And that is Bayes hypothesis. And it turns out this one actually maximizes these arguments. I mean, if you just sit down and think a little bit, that's not very difficult to see. And actually, another way to see why that is the case is actually see this error. And this Bayes error is the one that's achieved by this Bayes hypothesis. And now, if you let's compute this error in this case, what is going to be the risk of this is called Bayes? Is a H of Bayes. And then this one is an expectation, X comma Y, where H of a Bayes of X is not equal to 1. But then if you this expectation or distribution can be described as marginal distribution on X and the conditional distribution on Y. So if you refactor it in this way, and then we write this expectation, this means we are thinking about marginal distribution on X. So we are thinking on X components. And for each X component, we are thinking about the Y sample from conditional distribution. And then one, the same thing here. Now we can say, okay, how can we minimize in this term? And there are two possibilities. Y is either 0 or 1. And then we compute the average here. And the H of Bayes on X have to make a decision. So the sensible things to do, or minimum way to best way to do it is to pick, so in order to minimize this, pick one which have a higher probability, higher conditional probability. That appears actually in the calculation. This one is same as for Bayes case. Distribution on X, so minimum of D of Y0 given X and D of Y1 given X. That comes from the definition of Bayes, and then you can see that this is as good as we can achieve for any hypothesis. So this quantity is called there may be the Bayes error. Double check. This is called noise on X. So it's something as for particular X, something we cannot really do better. Okay, because the best choice is to pick Y that has a higher conditional probability, and so this is an error that we cannot avoid. So that's why it's called noise. And the expectation of this noise is the risk of the Bayes hypothesis, and this is called a Bayes error. And this Bayes error really describes how difficult the problem we have, how much noise that problem has. If the problem doesn't have much noise, it's easier to solve. The problem has a lot of noise, it becomes more difficult to solve. Okay, so that covers everything that I want to talk about for chapter 2. So at any time, you can ask any questions. But do you have any questions right now? I will wait maybe 10 seconds. There are nothing, then I will move on to the 2 exercises that I want to discuss with you. Okay, so then let's talk about 2 exercises. There was 3. So the first exercise is the question 2.10. So what this question asks us to do, it's suppose we have a problem, and suppose that we have a concept class C, hypothesis H. Suppose that this is peg runnable. So which means that there exists a hypothesis, the algorithm A and polynomial that satisfies certain properties. Now we want to use this A and polynomial and to find a hypothesis that that is consistent with a given set of samples. Okay. So what's the problem? The problem is construct an algorithm A prime that takes sample S, which is x1 and so on, xm, and its labels, which is y1 to yn, and such that each of the yi is computed by some hidden concept, which we don't know. Okay. Fixed C and C. So that's and then what we have to do, we have to return H that is consistent with this S and Y1 to. What does this mean? This means that the empirical risk that we compute with S, I mean Y is implicitly here, for H is equal to 0. So what we did before is that we said when we typically construct a peg learning algorithm, the situation was the other way around. We are given a learning problem, and we use an algorithm that produces a consistent hypothesis. In other words, hypothesis that satisfies this requirement, and then show that that algorithm is actually what's required in the definition of peg. Here we are doing the other way around. We have a peg learning algorithm, a polynomial bound, and then from the peg learning algorithm, we want to construct an algorithm that finds a consistent hypothesis with high probability. So this high probability means any of the measures that we care about, I mean the number of so suppose this is a polynomial time. So any of the measures that we care about, if we just run this algorithm a little bit longer, polynomial based on the polynomial time, then it will produce the good, will produce this consistent hypothesis with high probability. Okay. So I will give you maybe 2 minutes to think about this. So this make you get puzzled. I mean, maybe just parsing the exercise may take some time, but just think for yourself. I mean, try to understand this problem, and then maybe if you can come up with a solution, that's great. It's a bit like use A as a subroutine. So really what you have to do is use A as a subroutine and construct A prime. Then the construction of A prime may use this polynomial. This what it means is for any delta means this is polynomial prime. Just to such that median again so the exact statement is like what the one I wrote there. Any problem, any required precision, any number of sample is greater than polynomial. So then these things works. So actually, not actually these samples was wrong. So algorithm runs in polynomial time. Then the output of the algorithm is guaranteed. It's randomized algorithm, but its output is guaranteed to satisfy this property. So I think I made so many mistakes here. It's not about this. So the algorithm is a randomized algorithm. So there is a randomness in the algorithms, but it has a with high probability it returns this something satisfies this property. Okay, so how to solve this problem? And then here's an idea. So the way we can do, so we define this A prime. We take, say, x1, y1 up to xm and ym. Okay. Now what we do is we want to call this A to produce a good hypothesis. Okay. How do we call it? And we want to call, what we do is that we define uniform distributions. Let's say that the uniform distribution over x1 dx up to xm. So PEG is designed to work, PEG algorithm is designed to work for any distribution. So we are picking particular distribution d hat. And then for the heads, we are also defined. And let's see the function in concept class. So such that the C of xi is equal to y. I mean, that's the C, unknown C that I mentioned here. Then what should we do? Then from here, what we do is that we generate samples. Now pick a sample which, let's call it M prime, some examples. Shall we call it x1 prime, x2 prime, so on, and xm prime. Let's not use it m prime, different words. Use n examples. And from the head, which means that some xi, maybe x1 may appear repeatedly, but that's no problem. We just generate sample from here. Then let's y1 prime to ym prime be their labels, which we can also do because when we are given the label for every xi's. So then after this, what we would do is we have just called A with x1 prime, y1 prime, and xm prime, and xn prime, yn prime, and return its result. That's what we're gonna do. And the important part is, so it's really, we are given x1 up to xm, we are defining the distributions over x1 up to xn, and then we are generating samples from that distribution. Based on the samples, we just call the existing algorithm A. So that's the description of the algorithm. The important bit is not quite described here. The most important part of this description is this n, okay, how we should pick n. And then this n is chosen. So that's why the running time is have this polynomial thing. This n is chosen to be the following. So here. So n is chosen to be polynomial. So this polynomial is the one that's given for the algorithm, original algorithm, polynomial over 1 over 1 over 2m, and the 1 over delta and n. So then why this is good enough? The reason this is good enough to the reason this is good enough is that if we run this algorithm, because the A is pack runnable, so what it returns will satisfy the following thing, which is what it will satisfy is that it will return something P where the real risk of H the returned by prime by the algorithm is smaller than epsilon is 1 over 2m, so 1 over 2m with high probability. Yeah. Now this R of H H subscript S is defined over the uniform distribution. So we have a uniform distributions, and then we compute each error, and then this error is really this error with respect to this uniform distribution D hat is exactly the same as this empirical error that we are talking about. Okay, and then for the empirical error, because there are only m examples, if you make only one mistake, then and also it's a uniform distribution, the cost we have to pay is 1 over m. So to reduce this error to be smaller than 1 over 2m, we shouldn't make any errors at all. If we make one error, the cost is going to be 1 over m. So this cannot happen. So this statement is equivalent to, so that statement for original S, and this S prime, which is obtained n sample that we obtained here. So, and then this statement, these two things are equivalent. So that's why, so this means that the probability, but the return the hypothesis is consistent with all the samples is going to be small, at least 1 over delta. And so that's how you can design is pick this right number of samples. Okay. Now we have 5 more minutes. So then the next problem to talk about is this. For this problem is actually exercise 2.1. Then exercise 2.1 kind of tells us some other models of pack learning. This is something called the two oracle. Okay. So in this scenario, we say the concept class CH is two oracle pack runnable if there exists an algorithm, okay, and polynomial such that the following is true. And it's a bit tricky here. So there are for any two distribution, D plus and D minus. So the problem specification before was given by concept and concept and distribution over the input. So here it's defined different way. We have one distribution, two distributions over input. And for epsilon and delta or sample if so this algorithm can be randomized. So in this setup, it doesn't have to be deterministic. It can be a randomized algorithm. So if the usual condition is sample is greater than polynomial, one epsilon delta n. But there is another condition. So this d plus and d minus can be distinguished by some concept. So there exists some unknown concept C, such that you can distinguish example from d plus and d minus for any x if d plus x is greater than 0, that say C set is equal to 1, and any x d minus x is greater than 0, C say is 0. So there is a heat concept that distinguishes plus and minus. That is the case. So then so what algorithm does is that this algorithm A take S samples from distribution D plus and also so M samples from D plus and also M samples from D minus. So it gets positive samples and negative samples separately, and then you return on hypothesis. Then what the guarantee tells us, guarantee say probability over this S plus, which is sample from D plus M, S minus, sample from D minus of M, and then also randomness of the algorithm. So the probability that for all of these, the outcome of the algorithm have error. So it's a bit confusing, but for the plus case, okay, it just take time for me to explain the problem, but h of x is equal to 0. This means that for positive case, what's the output of the algorithm make a mistake that is bounded by epsilon. And similarly, for negative case, plus minus. So this is an error. Negative case, h of x has to return 0, but it return 1. Error is also bounded by epsilon. Both cases, both errors are bounded by epsilon with high probability. So that's the condition of these two oracle pack non-nullable. And then the question asks you to prove so that some concept C of H is 2 oracle pack. If and only if C and H is pack. So with randomized algorithm. So what it means is in the usual pack, we assume that the algorithm that solves this pack problem is deterministic, but here it can be randomized. And actually, the problem is that for H, we add 2 more functions, H0, which returns 0 all the time, H1, which returns 1 all the time. And that's the problem. Let me just give you 1 minute to explain the idea of how we can solve this problem. For 2 oracle pack, we're given 1 algorithm. Let's call it A and polynomial. And then for pack, you have a different algorithm, both randomized, A prime and poly prime. So in this direction means that using A prime and poly prime, you should be able to construct A and poly. Okay, and for the other direction, using A and poly, you have to construct A prime and poly prime. So from one, you need to construct the other. And then key idea, I mean, the A and A prime take a different interface. One take two sets of two samples, S plus and S minus in the above case. One below take only one sample, which is S. So what it have to do? So you have to, for the other direction, you take S plus and S minus. And then you have to design a certain way, but to plug in some S. And this S is actually obtained, one way to do this is you construct S by sampling each of the elements in the S plus or S minus random. So what I meant is there will be X1 plus X2 plus up to Xn plus, then X1 minus to Xn minus. What you can do is with probability half and half, you either choose the X1 plus or X1 minus, that's going to be X1. The same thing with probability half and half, you consider the second guy, pick the next one, X2 and so on. So that's how you can construct the one below. I mean, if X1 comes from the first, we mark it, label it 1. X2 comes from the second, we label it 0. And that will form the input to this the A prime, the algorithm. And that's how you can solve the one direction. The other direction is much more tricky, and I encourage you to think about this. And you have to do a bit more clever tricks to solve the other direction. And there are a bunch of other problems at the end of this chapter. And some of them are very conceptual. Some of them are simple application of what you learned before. So I encourage you to solve, look at these exercises and try to solve them. I found this 2.1 quite nice. And then also if you see very long question, that I also found very nice. Okay, sorry for going over time. And that's it for today.